Okay, so shall we start again?
Yes, sir.
Okay, so we were discussing the cyclic groups or cyclic groups. CN, and I wanted to make some comments on them. A very nice way of visualizing these groups is that you can think of CN as the symmetry group of an n-sided regular polygon with directed sides. Okay, so you can think of it. So for example, suppose that I have a pentagon, a regular pentagon. Sorry, my drawing is not going to be very good, but you'll get the idea. So this is a regular pentagon of sorts. Okay, so it's supposed to be regular, and it has directed sides, meaning that the sides have a given direction in the same sense. Okay, so the symmetry group of this object is C5. And what is C5? What is the generator? It's basically, rotation, say in the clockwise or counterclockwise fashion, you just have to choose rotation by 2 pi by 5, right? Around the center. So if this is the center, if you rotate it by 2 pi over by 5, then you get back the same shape. Okay?
Yes,
so
sir.
is it clear why this is C5?
Yes, sir.
All right. So let's do an example. So an explicit example. Now this example is a bit weird because it's actually, so it's C4. And we know that C4 is isomorphic to Z4. Now what is Z4? Z4, let's write it like this. Maybe it's a bit of an abuse of notation, but it's got 4 objects. So let me define what Z4 is. Sorry, somebody's drilling upstairs. So Z4 is a set of integers. The set of integers under addition modulo 4. Okay? So we say that if A is an integer, it's equivalent to B if A is equal to B plus 4n for n an integer. Okay? So this operation partitions the integer into 4 equivalence classes, and these equivalence classes are 0 bar, and they consist of the numbers separated from 0 by 4, the multiples of 4. And then there's 1 bar, which are separated from 1 by integer multiple of 4. Similarly, 2. And 3. Is it clear what I mean by this equivalence classes? Sorry, it shouldn't be 5, it should be 7. So what is a group operation? So if I take, say, 2 plus 3, what I have to do is that I have to pick some representative, right? So let's, I don't know, let's take from 2, let's take, say, 6. And then from, say, 3 bar, we take -9, right? So we get -3. So do we have -3 or -3 is here? So this is, so that means that, 2 plus 3 is 1, right?
So it's
is
like
this
we have a cyclical group and each element is an equivalence class, and they abide by the group laws.
Yeah, I mean, this is just, modulo addition, which if you are a CSE major or minor, or if you have done any programming whatsoever in life, you know that this is a thing, right? This is a thing you have to learn.
Yes, the 2 plus 3 is 5, 5 mod 4 is 1.
Yeah. So, okay, any questions?
So could you discuss C5 again, if that's possible, shortly?
C5, yes. C5 is the group of symmetries of this, of a pentagon with directed sides. So it is generated by a rotation of, say, 2 pi by 5. So one way you can do it is the following. You can take this shape and let's just copy and paste it below. So one way of thinking about it is you take this shape and you embed it in the complex plane, okay? You embed it in the complex plane in a way like this, right? I think it should probably go through there. Sorry, it's not a very good, so this should be the center. And then you say that, let's look at all the elements which are, look at the numbers which are e to the power I, 2 pi n over 5. Okay?
Is it related to the root of 1 unit 5 units?
Yeah, right. So n, where n is an integer, right? So n is an integer. So if you keep multiplying, the points by this factor, what will happen is that this guy will switch to this guy, right? And I'm probably not writing, sorry, I didn't draw this correctly. Because that wouldn't make sense, because that would be, if n was 1, so this is clearly I, so that's not going to work. So I definitely have not done this clearly. So what would be is something like this, right? It would be something like this. Maybe it'll be a little bit higher, right? Right. So you know, so this is going to be alpha. So alpha is this object. Sorry, alpha is not this object. Alpha is this object with n equals to 1. Okay, so alpha is going to be e to the power I 2 pi over 5. Okay, so what does alpha do is that it rotates every point by this angle, right? And if you have alpha to the power n, alpha to the power 5, then you get the identity, which is just a 1, right? The number 1 here. Okay, Nahi, does that make sense?
Yes, sir. I was just not sure what the group operations and all that was in this case, but it's fine.
Yeah, the group operation in this case is, so all I'm saying is that there's an isomorphism between, okay, C5 consists of alpha squared, alpha cubed, alpha 4, and alpha 5, which you identify to be the identity element. Okay, so this is the formal way. So the way that I've written it also includes the group operation, right? So essentially what I'm saying is that this is A, this is B, this is C, D, and this is E. So, and if I were to draw a multiplication table, I would have 5 columns and 5 rows. And so essentially, this would be, say, E, A, B, C, D, E, A, B, C, D, and then you can have E times E is E, A, B, C, D, E, A, B, C, D, and here you would have A squared, B squared, C squared, D squared, and then you have AB, AC, AD, and then BA, BC, BD, CA, CB, CD, DA, DB, DC, right? So this is the abstract, I haven't really, and then you're going to say that, okay, I'm defining the group in such a way such that E is alpha to the power 5. A is alpha. Okay? And then you basically fill in all these things, okay? And then B is alpha squared. Okay, so that's how you yeah, and D is so the way that I've written this over here implicitly is going to give you what the group multiplication table is, okay? Depending on how you identify these things, okay? Well, E, of course, you don't have a choice, but A, B, C, D, you have a choice in identifying whether you want to identify it with this one, this one, this one, or this one. So depending on this, you fill in this table. But the geometrical way of visualizing this is basically to take this shape and consider its group of rotation. Does that make it a bit more clear, or are you still confused?
No, sir, it's a bit clear.
Yeah, here, what we're doing is we're using an isomorphism, right? We are creating an, a very explicit, representation in terms of complex numbers, in terms of phases. Okay, any more questions before we move on to the next example?
So these 5 points are in a circle, right?
Yes.
So if the
They don't have to be.
okay.
They don't have to be, they just have to be equidistant from the center.
Oh, okay. So
They just
my
this has to be equal to this. Okay.
yes, sir. So my comment was, if there are n roots of 1, would that make a continuous group if n tends to infinity?
Yes.
Okay, got it.
Yeah, and that is basically the circle group that we were discussing before. The one isomorphic to the circle.
Okay, sir, got it.
Okay. All right, that's a very good comment. Any other comment or questions? So let me check the chat. How many groups are there? Did we define them all? No. How many groups are there? I think for finite groups, well, they're infinite families, but yeah, that's a very interesting classification. I am not an expert on that. And, you can look that up, the classification of finite groups. And they come in series, and then there are these exceptional groups. I think they're called sporadic groups. And so the idea of the sporadic groups and the analysis of the sporadic groups are very interesting. And I think that's how they discovered the monster group. So I'm not an expert on that, but you should look that up. Yeah, the classification of finite groups, I think, is a problem, was an outstanding problem, which was solved only recently, like in the 1980s or something like that.